Hello, my dears. So here we will continue with the temperature measurement and pressure measurement as well. In the temperature measurement here, we will study what is called resistance temperature device, RTD. In the temperature, resistance temperature device, it's converting the temperature to resistance this time. The temperature is converted to resistance. That's why we call it resistance temperature device. So in RTD, the relation between resistance and temperature is to be found from this equation, where the equation is calculating R, the output resistance, equal to the resistance at temperature T0. When we start, let's say we start at room temperature. At room temperature T0, we measure the resistance, it's R0. Now, if I put the sensor to measure certain temperature of T, that is going to give me a resistance of R. So that's how we can consider it. So the equation is given like this. R is the resistance measured at the new temperature. R node is the resistance at the old temperature into 1 plus alpha into T, the new temperature, minus T node, the old temperature, where alpha is known as the temperature coefficient of the device, of the RTD. The basic idea of RTD, what is the basic theory we are depending on to get the resistance change by the temperature? It's going to be this equation. R is equal to rho into L over A. So the change of temperature will change the properties of this equation, either L or A. So the change of these quantities is going to change R. Mainly, this is the idea of RTD. So the change of the properties of the material due to heat will cause change in the resistance of the output. Usually the RTD is positive temperature coefficient. Positive temperature coefficient means the change of temperature, the increment of the temperature. If the temperature increase, means the resistance will increase. Unlike thermistor, later you will see thermistor is something else. When we reach thermistor, we will talk about it. So when we calculate the equation, we want to use the equation R is equal to rho into L over A. A is the cross-sectional area of the wire to be measured. L is the length of the wire which to be measured, and resistivity is the resistance of the material. Certain constant for each material. Each material has its own resistivity. The characteristics of RTD based on the material used to make from, like for example, we are having here the most common RTD are platinum, nickel, or nickel alloy. So you will find the characteristics as you see here. Nickel characteristics is as you see, and copper is this one, with platinum is this one. What I care about is the change of temperature with the change of resistance. This is going to be helpful for me. So we like to have certain clear change in both sides so that I can measure a small quantity or a small change of temperature. Let us now go to the coefficient, temperature coefficient resistance, temperature coefficient resistance, TCR. TCR is to be calculated as R100 minus R node over R node into R100, where R100 is the resistance at the temperature of 100 degrees Celsius, and R node is the temperature at 0 degrees Celsius. So it seems like we are making certain relation between the two temperatures. We are getting the constant from these two temperatures, the temperature of 0 and the temperature of 100. So we are going to use them to calculate what is known as TCR, temperature coefficient resistance. So the platinum RTD usually made to have its output resistance as 100 ohm. Of course, you can find variety of resistance, but usually the platinum RTD is made such that its output resistance is 100 degrees Celsius. From there, we can use this equation to calculate the temperature, or can relate the temperature to resistance. So the temperature resistance, or the resistance at certain temperature, is equal to the resistance at 0 degrees Celsius, the resistance at 0 degrees Celsius, of course in ohm, into 1 minus temperature coefficient resistance multiplied into T. So again, this is the new temperature, this is a resistance, this is the resistance at 0 temperature, and this is the temperature, and this is the coefficient. So here he's making or showing the relation between R0 to R100, how the relation is linear. So which allowing us to use this equation without any problem. Let us look at this example. In this example, he said the platinum RTD PT100 is famous RTD, measures 100 ohm at 0 degrees Celsius. So when it's 0 degrees Celsius, the resistance was 100 ohm. And 139 ohm at 100 degrees Celsius. I hope now you catch the idea. At 100 degrees Celsius, the resistance become 139.1 ohm. Calculate TCR. We want to calculate the temperature coefficient resistance. Usually we use these quantities to calculate TCR, and we can use the TCR to calculate other values. We will see this in this example. So to calculate TCR, alpha is equal to R100 minus R0 over R0 into R100. We calculate to find that is 0.0039 1 per degree Celsius. Now, in the second part, he asked me to calculate the resistance of the RTD at 50 degrees Celsius. So at 50 degrees Celsius, we can use the alpha which we just calculate, because it's for the same case, for the same device. So alpha will not change. For the same device, alpha will not change. That's going to help us or allow us to use this equation, R50 equal to R node into 1 minus alpha into T. In the substitution, R at 0 equal to 100, and here 1 plus alpha, which just calculated, multiplied into 100. When we calculate, you will find the resistance 119.55 ohm. And the last part, he said the temperature when the resistance is 110 degrees Celsius. We are going to repeat the same thing. The temperature when the resistance is 100 degrees Celsius. The same thing, but the other way around. Means we are given, or the resistance is given, we need to calculate the temperature. So here 110 equal to 100 into 1 minus the coefficient into T. What I want is this T. So when we calculate, this is one equation with one unknown, we can calculate T to be 25.58 degrees Celsius. For the construction of the RTD, it's made by a different technology. One of them is a wire made of certain material, which platinum most of the time, wound on a mica and protected by stainless steel. It's protected with the stainless steel. In the construction of the RTD, we have to keep in our mind that the heat is supposed to be transmitted to the sensitive element, and in the same time we have to make it such that it's mechanically strong. For that, we are putting the sensitive element inside the stainless steel tube, which is going to protect it against the mechanical action, and it will transfer the heat without problem. In the thin film RTD, the material, or the sensitive material, is made of platinum, and the platinum deposited on a certain element, as you see here. So here is the material, the sensitive material, which the platinum, as I said, is deposited here. We keep space for it here, as you see, resistance trim area. Now the terminal are connected to the lid to get the signal to the outside, because the change of the resistance here due to heat will be transmitted to the output. The whole device will be coated by certain material like a glass to protect it, as a coating to protect it. So that's how we are dealing, or that's how we get the construction of this type of RTD. So there are actually a variety of techniques used, but I selected these two, which is the wand type and the thin film type. We call it thin film type because we deposit the platinum on this surface. The self-heating of RTD, or RTD self-heating, one of the problem in RTD is when we want to convert the resistance to voltage, we are going to allow, we are going to let current flow in the RTD. If I want to get a very simple circuit to make you clear about this, if this is the resistance and here is the RTD, so the voltage here on the output, if you remember when we convert the resistance to voltage, this kind of circuit is converting the resistance to voltage. This is very simple one. Of course, we always depend on the Wheatstone bridge, but this time I'm going to use this one just for a matter of simplicity in calculation. So the current flowing here in the resistance is going to cause voltage on the output. Remember, this is RTD. This one is RTD. So current will flow to make a voltage drop. Now the change of the resistance, the change of this resistance due to heat will make change in the voltage applied, because current is flowing, the resistance is changing, that means the voltage will change on the output. So we are going to get a voltage on the output proportional to the change in the resistance, which is proportional to the change in the heat. The problem is the current flowing in the RTD by itself going to cause heat for the RTD. So in this case, the measured voltage is measuring the heat due to the device I want to measure its heat, and there is another heat due to the flowing of the current in the RTD. The solution for this problem is not to allow high current to flow through the RTD. So usually RTD will not accept, you are not supposed to allow a current flowing in the RTD more than 1 milliampere. So the limit is 1 milliampere. How this can be? By putting the resistance here, this resistance with this resistance, this RTD. So when you are designing the circuit, you will make it such that the resistance here going to limit the current. So if let us say the resistance here 100 ohm, here you are supposed to put a resistance which high enough to limit the flowing of current. So if the battery here equal to, let's say, 2 volt, so make it such that the resistance of this one and RTD will make a current flowing here less than 1 milliampere. In the sensor circuit, because we have to consider another element here, we need to keep in our mind that in RTD, or in the measurement of temperature, we are going to use Wheatstone bridge to convert the resistance to voltage. Usually that's what will happen, and usually the RTD is placed in the location we want to measure its temperature. Let's say in industry we are going to put it in the oven, for example, which far from the control room. In the control room we are going to have the bridge which is going to convert it to voltage. So for that, if the distance between the bridge and the RTD is long, that means the resistance of these wires going to affect our measurement, because the resistance between this terminal and this terminal is not only the resistance of RTD, it's the resistance of RTD plus the resistance of this wire and the resistance of this wire. In this case, we have to find a way to avoid this problem. We will make it such that the resistance of these two wires are not going to cause a problem or not going to cause error in the measurement. For that, we have a 3-wire configuration. In a 3-wire configuration, we are going to connect, as you see here, a point or the wire, one side of the wire, which wire A is going to be linked to R3. and wire B is linked to RTD. And if you notice now the branch, the legs of the bridge going to be, you see, I will depend on the color to explain it. This is going to be one leg, and this is going to be the other leg. Now, if I consider this idea, what will be the situation? You are going to find that RTD plus RB supposed to be equal, if I assume the other two are equal, supposed to be equal to R3 plus RA. Now, for the wires, because wire is having the same length, the wire which carrying the current to the RTD is same as the wire which having the current back. So if A have the same length as B, that means the resistance of A equal to the resistance of B. In this case, we have no problem no effect for the RTD on the circuit, because what will remain is RTD and R3. So we make it such that the effect of A is going to eliminate the effect of B. How about C? How about the wire C? The wire C have no problem because it's carrying no current. Wire C is carrying no current. The current is carried by A and B. That's how the current will flow. But C is carrying no current because we are going to, or not carrying no current, carrying very small current. It's carrying very small current, which is not going to cause effect on the measurement.